Welcome to today's lesson. We are going to look at sound, nature, and sources. We start by defining sound, where we say that sound is form of energy that originate from vibrating objects. It is a longitudinal mechanical wave. When we talk of mechanical wave, it means that it requires medium for transmission, as seen in our topic of waves. Some sources of sound. The first one we are going to look at is vibrating wooden strip. Now, if you have a meter rule or a piece of wood that is fixed on one end, and then you strike it sharply on the other end, you find that it will vibrate, and as it vibrates, it produces sound. You can be able to see it vibrating. Then we have vibrating wire, e.g. guitar wire being plucked. This one I'm sure you have ever done. When you are playing your guitar, or you have a wire that is fixed on two pieces of wood, and then you pluck it, it will always vibrate, and after vibrating, it will produce sound. Then vibrating drum. If you're having a drum, and then you put some grains on top of that skin part, and then you beat your drum, you will find those grains jumping up and down. That is a clear indication that the drum skin is vibrating, and that is why there is sound. Then we move to tuning fork. If you look at the diagram that we have here, a tuning fork has prongs. There are two of them. So for it to produce sound, these ones or the prongs are hit against a hard surface. As they are hit against, or they strike a hard surface, they move, they vibrate. As we have seen in this diagram, they vibrate to and fro. And as they vibrate, if it moves towards this direction, it will compress the air particles that are here. The air particles will be brought together, and that region will be transferred to other air particles. So here we will have particles that are close together, then followed by particles that are far away here. Then the process continues, particles that are close together. So when the particles are very close together, as we are going to see later, the pressure will be high. So we have a region of high pressure, a region of low pressure. So where the particles are closely packed or they are close together, we call that part compression. And when they are apart, like in this position, we call it rarefaction. Then we move to another source. We have vibrating air columns. If you have a bottle or you are having a test tube, and you blow across the opening, you will find that it will produce sound. So what you are doing is that the air particles that are within there, by blowing, you are making that air column to vibrate. So as it vibrates, it produces sound. Then we have air siren. If you look at our diagram, the air siren that is found in ambulances, you will find that it has holes. The holes are equidistant from the center. So if we take the first ring of the holes, the distance between each hole is the same. You take the second ring. So what happens is that this part is rotated at a constant rate. And when it is rotated, air is blown through the holes. When it is blown through the holes, the air particles will vibrate. And at the end, it will give us sound of a given note. Then we have the voice box. You may ask yourself, how do human beings produce sound? The answer is here. Human being, or what we call the voice box of human being, contains vocal cords. And these are the ones that vibrate. And at the end, they give us sound. Then we move to cog, wheel, and card. We have a diagram here. You have the wheels. So as it hits this stiff card, it will make it vibrate and it will produce sound. The teeth of the rotating wheel strikes the card, producing the sound. If the teeth are equally spaced, the wheels with the fewer teeth produce sound of lower frequency. Sound of high frequency implies high-pitched or sharp sound, and this we get it from air siren, football referee's whistle, and chirping of birds. Those are just examples. Then we move to propagation of sound energy. How is this energy moving from one place to another? So we go back to our tuning fork. We have seen that by vibrating the prongs, it produces the areas of high pressure that we call compressions and the areas of low pressure that we call rear functions. We have our diagram here. As the prong moves from A to B, it is moving like this. It compresses the air particles, and the air particles that is just next to the prong will have a high pressure. But as it moves, we will have now an alternate areas of high pressure and low pressure, as we have this in our explanation, that as the prong of the tuning fork moves from A to B, it compresses the air molecules, and this will transfer energy to the molecules in the direction where the compression occurs. A higher pressure region is thus created. Remember, if you go back to Form 1 work, we define pressure as force per unit area. And this force is given by weight. So if you have many particles of air together, then the mass will be high, and then finally you will have a higher weight. So when you have a higher weight, then it means that the pressure will be high. Now, when that pressure region, high pressure region is created, it leaves a region of low pressure on the left of A. Then the prong moves to A and then to C, and the process is repeated. So we shall have a series of compressions and rear functions produced, and this now will transfer energy to the air particles to the left and right. The energy transfer alternates in direction, just as the motion of the prong. And now, this describes a progressive sound wave in air that is traveling in both sides, as in figure below. We have the pressure change, and this now is the direction. So in here we have the region of high pressure at maximum. Then we have a region of low pressure. The region of high pressure is written as C, that is compression. A region of low pressure where the particles are far away, we are calling it rear function. So they alternate high pressure, low pressure, like that. This means that now our sound will just move the way the compressions and the rear functions are being formed. The direction of vibration of particles is parallel to the direction of movement of sound energy. Note that the particles are moving like this, and the movement of sound energy is also to the same direction. So since now the vibration of particles is parallel to the movement of sound energy, then we call sound energy a longitudinal wave. And a longitudinal wave is comprised, or it consists of compressions and rear function. Sound requires a material medium for propagation, and this makes it to be a mechanical wave. We move to experiment, and this experiment shows that sound requires a material media to travel. And this answers our first question in our introduction. Remember, we asked, do you know that there is no sound in space? Yes, because when we go to the moon, there is no atmosphere. There is vacuum. And as we are going to see through this experiment, we shall see that sound does not travel in vacuum. So when you go to the moon, because there is no air particles, then sound cannot be propagated, it cannot be transmitted. And therefore, even if you have your piano you are playing, then you can't hear that sound. We move to apparatus. We have electric bell, switch, bell gas jar, vacuum pump, wires, cells, and glass plate. Procedure. Set the apparatus as shown in the diagram below. This is our diagram. You see it is connected to the source of power. And we have the switch. These are batteries. Then we have the cock. Inside here we have a gong and a hammer. This is where the heating will take place. The vibration will take place through heating. And this is where now the sound will be produced. Again, if you look at this, we have the bell jar, the rubber cord, and the flexible wire. So this pipe is pumping out air. In other words, we want to create a vacuum so that now we can be able to see whether we can hear the sound of hammer hitting the gong. We move to the next procedure. Close the switch and observe what happens. Now, because we have not pumped the air, so there are still air particles inside our jar. So by closing the switch, we are making the circuit to be complete, and therefore the hammer is hitting the gong, and that will make it to vibrate, thus producing sound. So our first observation will be that the bell begins to ring and the sound is heard outside. Then step number 3, gradually pump out some air and note the effect this has on the sound reaching you. Now we want now to remove the air inside our jar and see what will happen when we close the switch. The intensity of the sound decreases gradually, or in other words, your sound becomes faint. Then procedure number 4, pump as much air out of the jar as possible and listen to the sound produced. Now that you have removed a lot of air particles, you have created some vacuum. And therefore, it implies that vacuum will not be able to transmit or propagate sound. So our observation will be, sound is found to have almost disappeared, though the hammer is seen vibrating. Remember, your switch is on, so there is complete circuit, and therefore the hammer is still beating our gong. So the hammer is seen vibrating, but the sound is disappearing. We move to conclusion. The above observations shows that the sound cannot travel through a vacuum. It needs a material medium for propagation. Then we move to factors affecting the speed of sound. We have the first one, temperature of air. Sound travels faster in hot air than in cold air. Why? Because as you increase temperature, the density of air decreases. Remember, in force, topic in Form 1, we defined density as mass per unit volume. So if you have many particles in a small volume, the density is high. So as you increase the temperature, the particles will expand and move away, and therefore that will reduce the number of particles in a unit volume. So the density will be decreased, and this now will increase the speed. As you can see, sound travels faster in hot air than in cold air. Then we have humidity of the air. The velocity of sound on air increases with the humidity. So this humidity again is decreasing the density. And when the density is decreased, then we have that the sound or the speed of sound is increased. Then we have number 3, direction of wind. If you are talking and the wind is blowing the same direction as the sound, then that velocity of sound is increased. But if you are talking or you're producing sound and the wind is blowing against the direction of the movement of sound, then again you'll find that your sound may not reach your destination. Then finally we have the density of air. The denser the air, the lower the speed of sound. Sound travels faster in solid, followed by liquids, and then gases. And we need to ask ourselves why. The answer is just here, the density. So we have speed of sound in materials varies from solid to solid, liquid to liquid, and gas to gas, depending on the density of the material. We have seen that the denser the air, the lower the speed. So the denser the material, the lower the transmission of the sound. So sound travels faster in denser materials. We can be able to see that in solids, it has higher density because the particles are closely packed. But in liquids and gases, the density is less compared to that in solids. So in solid, the speed is almost 6,000 meters per second. In fresh water, it's approximately 1,400 meters per second. And in salt water, we have 1,500 meters per second. So we conclude by saying that denser materials transmit sound faster. Assignment. If you look at this assignment, you're supposed, like the first one, to describe a simple experiment to illustrate that sound is produced by vibrating object. These are something that are in the notes. So don't recopy, don't go back and recopy. Evaluate yourself. Let the answers come from your mind. Remember, you are here to gain and retain knowledge. Before you even attempt the assignment, you can try to teach your peer and see whether you have grasped all the concept. So thank you, and let us meet in our next lesson.